In this video, we are going to learn which issues can arise related to grounding of a PV system. As we will see, these phenomena decrease the performance of the PV panels. In particular, we shall look at leading leakage currents, potential induced degradation, TCO corrosion, and the effects of islanding on safety. A PV module is formed by different layers. A glass layer is on the top part and it lays on a substrate, and the photovoltaic cells are situated between these two levels. The PV module generates an electrically chargeable surface area which is next to a grounded metal frame. Such an arrangement behaves as an electrical capacitor whose capacitance is greater the larger the surface area and the smaller the distance from the grounded frame. This capacitance is undesirable and it is referred to as parasitic capacitance. The parasitic capacitance is given by the relation shown. Epsilon naught is the vacuum permittivity or electric constant. Epsilon r is the relative static permittivity and it depends on the medium. A is the cross-sectional area of the capacitor and D is the distance between the two charged layers. As we saw when describing the overall configurations of the inverter, a transformer-less topology lacks the galvanic isolation between the PV array and the grid. In this way, the PV panels are directly connected to the grid, which means that there is a direct path for leakage ground currents caused by the fluctuations of the potential between the PV array and the grid. The value of the capacitance is also dependent on the atmospheric conditions, mostly dust and the humidity. The top of the module, which is covered with glass, is non-conductive when clean and dry. On heavy rain days, this part becomes conductive due to presence of water and mineral salts accumulated on top of it. The effective area of the capacitor increases significantly, causing the capacitance to increase. Leakage current or discharge current is a reactive current with its phase shifted by 90 degrees to the grid voltage. This means that this current is lossless and not dangerous on its own. However, this current can superimpose a possible residual current and obstruct its detection by safety devices. Potential induced degradation is a phenomenon that occurs when the voltage on the module and the leakage current act as a driver of ions within the module. The PV system and the environment interact to cause PID. This is due mainly to the fact that humidity and dust on the panels can cause sodium ions to affect the performance. Let's take a PV system connected to the grid via an inverter. The neutral point is in the middle of the system, so a positive pole shows a positive potential or a voltage against the ground. In a similar way, there is a negative pole. Typically, the last cells have a potential of minus 200 to minus 300 volts, depending on the length of the string and the type of the inverter used. The frame of the PV modules must be grounded for safety reasons. This means that the frame has always a 0-volt potential. Potential induced degradation occurs most commonly in the PV module that is closest to the negative pole. The ions are driven from the semiconductor material towards other elements of the module, like glass, mount, and frame. This effect causes the module power output capacity to reduce because the polarization can adversely alter the characteristic curve of the PV cells. The curve tends to become more flat as the degradation effects increase. The open circuit voltage and the short circuit current remain nearly unchanged, but the maximum power point can be reduced up to 70%. There are different ways of reducing the PID. One method is to use a polarization neutralizer that applies a reverse voltage to the affected pole overnight. This solution is preferred when the array cannot be grounded because of the inverter chosen. If grounding can be performed, we have to differentiate between the two cases. If the wafers of the PV panel are N-type, then the positive pole should be grounded. On the other hand, if the cells are of P-type, the pole to the ground is the negative one. Another phenomenon observed in the past, even after short operating times, is the corrosion of the so-called TCO layer. The TCO, or transparent conductive oxide, is a layer present in thin film PV modules. It is used to allow electronic conduction without the application of front and back contacts. Two designs are usually taken into account: the substrate design and the substrate design. The difference is in which order the different layers are structured during the production process. In the superstrate design, the TCO is in direct contact with the glass. This means that this design is the most affected by TCO corrosion because the sodium that is contained in the moisture on the cover glass enhances the corrosion of the TCO beneath. When this electrically conductive layer is damaged, it cannot be repaired, and this results in substantial power losses. As a countermeasure, the leakage currents should be reduced. It is possible, for example, to increase the distance between the cell and the frame to reduce the flow of ions. It is also possible to use galvanically isolating inverters together with a negative grounding of the PV array. In this way, the positively charged sodium ions are repelled from the TCO layer, preventing corrosion. Additionally, module manufacturers are developing measures to prevent this effect. For example, by improving the sealing of the module edges, the penetration of moisture is prevented. This helps removing the basis of the corrosion process. Islanding is related to grounding and the protection in PV systems. Some potentially dangerous cases may arise. For example, if the electricity grid is down for maintenance and some operators are working on the distribution lines, but on the same street a PV system produces power. Without any protection, the power will be delivered to the grid, putting the workers in a serious danger. In order to avoid this, islanded or a no-grid condition must be detected by the solar inverter. This condition is checked at the AC side, and the inverter shuts completely off the PV system. To sum up, in this video we saw some issues related to grounding of PV systems. Leading leakage currents derive from the parasitic capacitance in the module. Potential induced degradation is given by the high potential difference between the module and the frame, which is grounded. This causes a current to flow towards the frame, which results in considerable losses. TCO corrosion regards mainly thin film modules and leads to a reduction in the module's performance. Lastly, we saw that no-grid detection is a required feature for grid-connected inverters in order to avoid safety issues.